into the profile. And in 2D it's the opposite. So when we go to 2D later on today, we actually see that we need to plug in positive values if we want to kind of infiltrate water into the soil. But basically what you see when we look at the cumulative flux, you don't see it very well, but initially you have like a steeper kind of slope, which means initially water kind of infiltrates at a faster rate. And then as soon as the surface layer is saturated, it actually slows down a little bit, and then you have like this linear kind of constant infiltration rate with time. So this was the first problem. Then the second one, I think we also did the second one.
Is that the rate? Okay. Does it matter what type of soil it is where you have the increased?
Oh, sure. I mean, this is again like it's completely dependent on the hydraulic conductivity. So when you have lower hydraulic conductivity, so when you have like this was a loam soil.
Mm-hmm.
So if you would have like a clay loam, even a finer soil, the kind of slope initially would be smaller. Okay. But still, you would see similar behavior. Only the slopes would be different.
It's something different, but then it becomes linear after once it becomes saturated.
And this is really why, because initially we have relatively minus 100 centimeters, actually not relatively dry, but we have partially saturated soil. So basically initially, until the surface layer gets saturated, the infiltration rate is higher. And then as soon as the surface layer gets saturated, water moves through the profile, you actually get this constant infiltration rate. And of course, it also depends on the pressure head. Here we said zero pressure head. Basically, this is equivalent to applying water, equivalent to the saturated hydraulic conductivity. If we would kind of specify like 2, 3 or centimeter pressure on the surface, we actually might exceed the hydraulic conductivity. So we have like additional bonding, and this actually might lead to instability of the simulation. And we see this a little bit later on when we actually impose fluxes. That when we generate too much of a gradient, so when we force like boundary conditions on the system, and we generate too big of a gradient, then the solution doesn't converge, and we need to find some other kind of creative ways to resolve this. So this was this first problem. Then we also did the second one, where we basically now switched from we actually started out with a little bit drier soil. So instead of having an initial condition of minus 100 centimeters, we had minus 330, which is equivalent to field capacity. And field capacity really when you kind of, when soil is saturated due to, or gets saturated due to irrigation or due to precipitation, then irrigation or precipitation stops, you have internal redistribution. So water due to gravity is going to move downwards until the water content remains almost stable. And this is, it's not really a very good physical concept, but for agricultural purposes, we always kind of define this field capacity at minus 330 centimeters. Of course, strictly speaking, it should be really dependent on the soil texture. But this is like what you use in agriculture. So when you irrigate, you see a rise in water content, and then it drops down, and then it reaches this almost constant level, and this is approximately around like minus 330 centimeters. So we started out with drier conditions. Then, of course, again, when we look at this, so now this would be like the second case, where we start with minus 330. And that means we start out with a lower water content. So we start out, so if we go up here, we had like, the first one was at 100, 330 somewhere here. So we start out with a water content of 0.16. Then again, we see completely the same behavior. So water reaches 26 centimeter depth first, and then it takes some time, so there's a time delay, and then basically the water content ramps up 50 centimeter depth, and again for both cases after some time we basically reach full saturation. And there is only like a really very, very small difference when we compare the cumulative fluxes. Now, because the soil is drier, actually the fluxes are a little bit higher initially and also throughout. So the cumulative flux, so this would be like for our first case, and then you see that we have a little bit, it's very, very small difference, but the fluxes are a little bit high, and again, negative fluxes. So a larger negative number means higher flux. So this was the second case. This is only, of course, like a difference in water content initially, when we look at those depths. Then we said, now we are kind of moving away from the pressure boundary conditions, and first we, this is how far we actually got. So now instead of imposing a constant pressure head on the surface, we impose a constant flux. And we basically said we're going to use loam soil, and the flux that we're going to apply is equivalent to the saturated hydraulic conductivity. So when we look into hydrus, we saw the hydraulic conductivity of loam is 1.04 centimeters per hour. And now, of course, because I know that it wouldn't really make a lot of sense to kind of plot fluxes because it's constant, so we only would take a straight line of at minus 1.04 centimeters per hour. So now we said we're going to plot pressure heads instead. So, and what you see, so we basically plot the pressure head with time, and what you clearly see, so again, we start out with, so we started out with minus 100 centimeters, so we switched back again to minus 100 centimeter initial condition. And then you see actually the pressure head ramping up relatively fast until the soil gets saturated on the surface. And then the soil remains saturated. But what also happens, what you see, not all water actually can infiltrate. So you have a buildup of pressure head, then there is a release, and it's at zero again, and then you have buildup of pressure head. So this already is a good indicator because the hydraulic conductivity is exactly the same of our imposed flux. You see that there are already some issues here. It is actually already the first indication. When you, for example, increase the flux again, then probably this simulation is not stable anymore, and we don't get the result. So this is how far we got. And the next thing we want to do is, I hope everybody still has the instructions from last time. If somebody missed the instructions, there's a few more. Those are actually updated ones because they updated the number 10. Oh, maybe one.
So the one that you gave out last week, you say there's an update to?
Yeah, it's only for kind of over 10.
For column 10. Okay.
Because I realized there was a change of functionality in the very latest hydrus version. So it wasn't really necessary to do all the hocus pocus we did last year. So we can impose those boundary conditions in a much simpler way.
Sorry.
So now basically we are moving to problem 4. So problem 4, we only want to repeat problem 3. So kind of constant flux boundary, initial condition of minus 100 centimeters. But now we want to apply half of the flux. So basically the flux that we apply is half of the saturated hydraulic conductivity. And then we do the same thing, and then we double the flux. We'll see what's going to happen then. So let's do this. So if you open, I hope I still have this last week. So you, of course, also should get it on your computer. So let's go back to 3 quickly, and then we'll look at 4. So again, hopefully everybody remembers how hydrus works. So we start out with the main processes. We only want to model water flow. We need to specify length units. So we kind of use centimeters. And then we also need to specify the number of materials. So we have a uniform soil profile. So we have one material. We don't have any solid transport calculations, so we don't care about mass balance. And you also want to simulate in the vertically, for a vertical case, so the vertical basically we need to plug in 1. The depth of the soil profile is 200 centimeters. Then we said we want to simulate in hours. Simulation should go over 24 hours. We don't have any time variable boundary conditions. And we really don't change this kind of time steps unless we get really into troubles with conversions. So then we go, then we need to specify the print time. So we basically want to have a result every hour. So if we simulate over 24 hours, we need 24 print times. So this basically gives us results on an hourly basis. We don't really mess around also with the iteration criteria unless we run into troubles with convergence. Then we said we take a very simple case, Van Genuchten parameters of Van Genuchten soil water characteristic model, no hysteresis. We do this, let's see what was loam, so we do this for loam soil. We impose a constant flux when we, and the free range on the bottom. Initial conditions we specify in terms of pressure head. So when we go to next, we need to specify the upper boundary flux. And I mentioned last time, and this is really important for hydrus 1D fluxes into the profile, they're always negative. So positive flux would actually mean like the evaporative flux. And if we would apply an evaporative flux to partially saturated soil, we also generate a situation where we have a very high gradient at the surface. And I think if we would run this with positive 104, it also wouldn't really converge. So it's really negative. But then when we go to hydrus 2D, it's a little bit different. So it's the opposite. So positive fluxes into the soil profile. So this is basically the imposed flux on the top boundary. Then we go next. Then we always move into the profile application. And where we can specify everything, so conditions, we can specify the material distribution. We don't need to change anything because basically we have a round, uniform round soil profile. So there's only one profile. Then we also can actually change the profile discretization. For this, it's good enough. So we have 2 meters. We have 101 nodes. Basically, we have like layers of 2 centimeters, which we say is good enough. Then we have initial conditions that we specify, like we initially indicated in terms of pressure heads. And again, we don't need to change anything, so we have like uniform minus 100 centimeter initial pressure head throughout the profiles. Those are our initial conditions. And then when we go to boundary conditions, we don't really need to specify any boundary conditions because we already imposed this. This was a little bit different when we had like a constant pressure boundary condition, so we assumed basically uniform minus 100 centimeters initially. And then only at the very top, the surface, we kind of put it to 0. This is okay. Then we also inserted observation points. So we said one observation point was 26 centimeters below the surface. And this is also a little bit different when compared to hydrus 2D. Here actually the soil surface is 0 elevation, and for hydrus 2D it actually starts at the bottom of the profile. So we would get 0 at the bottom and 200 on the top, but we'll see this later on. Then with the second observation, know that 50 centimeter depth, so we have everything set up, and then we basically ran the simulation. And you can double check actually like this table. So you have the layers, you have the initial conditions, we don't have any root water uptake, we do not deal with scaling of hydraulic functions, and we have each of those layers, we have material 1, and we only have 1 layer, so it's layer 1 throughout. We don't really need to double check. It is basically only the information we have in the visual and the publication presented in table format. Okay, then what we usually do is start calculation, execute hydrus. So okay, because this is a really small problem, we get results very, very fast. The center, and then we basically have our results. And we kind of open the observation node file to kind of extract initial water condense, and then the T-level file to extract our pressure head distribution, our fluxes. So this was how far we got. And then the only thing is we want to do is we want to save this. File, save as, so we go to the next problem, PO4. In my case, so we have a huge loop. So we have to do problem 4. And here probably tells me that I will save it. But you need to save it. So I only open this, or I can open to this. Go here, into read, PO4. And it should allow to save it. Okay, so now we said we keep everything the same. The only thing we change is the boundary flux. So instead of using a boundary flux that is equivalent to the saturated to hydraulic conductivity, we use half of it. So instead of, I think it was 1.04, we go to use 0.52 centimeters per hour. So the only really thing we need to do, we need to go to the boundary conditions. We say constant flux, and we go next. And here we change from minus 104 to minus 0.52.
So leave it as free drainage on the bottom, on the lower boundary condition.
Free drainage, we keep everything exactly the same. So the only really difference from example 3 is that we now reduce the influx into the soil. Okay. And we don't really need to do anything else and only run it, because we have all the information from problem 3. Very fast. then we can look at this in hydrus. The only problem is when we want to compare things, it's when we want to plot like two cases on one graph, so we almost need to avoid it. We can look at also at the observation nodes. And the graph we actually want to see in Excel would be time versus water content. So you basically see that now for long and for the smaller flux, it takes actually more time until we reach 26 centimeter depth. And then also when you look at the increase, it's a little bit more gentle, so the slope of the water content increase. But we'll see this better when we actually plot it. But we can get, the only thing I want to show is we can get also this information out of those graphs. And then we said we also want to plot the head on the surface. Now we impose a flux, so we want to plot the surface, pressure head on the surface. And again, when we compare this to the other case, we basically see a little bit kind of lag time in terms of response, and then it also went up a bit fast.
But it's not doing that variations as you get closer.
No, you see, this is really one. You know why?
I do not.
Think about it. So what did these variations indicate in the other case? That we actually cannot infiltrate all the water that we apply. So in this case, because the flux is actually only half of the saturated hydraulic conductivity, there's absolutely no problem for the soil profile to take out all the water. So that's the reason. In the other case, so it gets saturated, then there's a little bit of increase. You actually have a positive pressure head. And then, for some reason, the simulation somehow managed to infiltrate the water. But you see towards the end those kind of jumps get. This actually is already the first good indicator that something happens with the stability. And this is really because we said when we kind of impose like constant head or constant flux boundary conditions, those are like system-independent boundary conditions. So we really force something on the system, and we don't really consider the reaction of the system. That's the reason in these cases actually would be much better to use like system-independent boundary conditions that are generated by the system or by the simulation, and basically consider the change in soil moisture. Then we said we have actually different scenarios. We can have atmospheric boundary conditions with runoff. So that means as soon as we exceed like zero pressure, water is removed from the system. But then we also have a case or an option where we actually can force water to infiltrate, so that we can allow water to bond up to a certain depth. And then only it infiltrates at the later time. But this is usually when we impose something on the system and we don't consider the reaction of the system. This is where we can get easily those very high gradients, and this is in some cases hydrus substrate. So, okay, so let's import this into Excel. And we'll go to our Excel sheet. So we said first we actually kind of need to open this observation node file. So open hydrus on my desktop. Go through problem 4 files. So there's this node information output file. Said we want to limit it, then we have a separation space, finish. Here we basically have the depth increments, that of course we need to go from 0 to minus 202 centimeter increments. And then we have, oh, this is the wrong file.
Yeah, you got the node info there.
The node information file. go this one quickly. Observation about this is the right one. Now we basically have the time interval, and then we have the water content of 26 centimeter, which is equivalent to node 14 when we go on the surface, and then 50 centimeter, which is node 26. So we can go through this.
Can you hold them there? Can you do that? That there?
You kind of, so I start again. So the first thing what this do is press shift, then end, and arrow down. Then you release the shift kind of key, you go up again, then you push the contour key and mark the first one. Then you release the contour key and go back to the shift key and do the same end downwards. Then we go back to the contour key, oops, up again, mark the first step, then again we switch to the shift key, and this way we basically copy all three ones. Copy. Then I only left those first two when I did the simulation the time this morning. So I only want to go to the first cell and then I will paste special 1 or 3. And now we immediately see the moisture profiles. This is what we saw initially. So this was case 1, where we had a higher kind of flux at the boundary. So you see that when we have a higher flux, it actually reaches, of course, the 26 centimeter depth. A few hours before that, it reaches the 26 centimeter depth when we only have half of the flux. And then also when you kind of look at the slope, so when we have higher flux, so the water content changes much more rapidly than when we only have half of the flux. Then of course we see the same behavior. It's time delayed until it reaches 50 centimeter depth, and then you basically also see this little bit gentler slope, which basically only means that the conditions change a little bit slower. And this is really because in the first case, so the solid lines, we apply water at the higher rate, at 104 centimeters per hour, and in the second case, we basically apply water at a little bit lower rate, or half the that's the way we see this behavior. Then we open the P-level file. Here we only want to see the age of the top. Age top here. So we want to copy the time step. So here you basically see we don't really see those fluctuations. And There's also an indicator that we never really, we get very close to zero pressure head, but we don't get all the way up because, again, the infiltration capacity of the soil is basically double as much as we apply water on the surface. So that's the reason we don't go up all the way.
So there's some value where you can actually zero that out, where you're not, where we get the flux. Right now, I mean, we see
the flux is constant. So in this case, for the red case, this is the pressure head. So for the red case, the flux is 0.52 centimeters per hour, which is half of the saturated hydraulic conductivity. That's the reason you don't see any pressure build up on the surface.
Mm-hmm.
So it's always a little bit below zero pressure.
Right.
Zero pressure would mean like water starts building up.
Building up over top of it.
But since we can infiltrate everything, it never really gets there. It gets very close, but it never gets there. So the redistribution of water is basically faster than the application of water. That's the explanation for this. And then for the other case where the application rate is exactly the same as the ability of the soil to contact water, you see that sometimes depending on the iteration, you get pressure build-up. But then the program recovers, so it infiltrates it and pressure builds up again. And initially, you basically see that this is not that big of a problem.
Okay. Really?
But then as the layers get separated step by step, you actually see that this changes the pressure on the surface. This is already a good indicator that there is some kind of instabilities here. So now we do exactly the same, only instead of half of the flux, we apply double of the flux. We'll see what's going to happen then. So we save this.
That becomes really unstable.
Then we go back to the values. We now only save this. I will save this. This would be not 45. Then the only thing we really change, so everything is the same, we go to the boundary conditions, constant flux, go next. Now instead of minus 0.52, we put in minus 2.08. So double of the saturated hydraulic conductivity of the boundary, 2.08. So okay, this is really the only change we make, and then we try to run it. So now what we see, yes?
No, no, I figured about that this morning.
And now what we basically see, now we have really too big of a gradient on the surface. So hydrus doesn't really converge. Now, last week we talked about some potential remedies. And we'll try a few of them and see if we can get it to run. So the first step, you always want to increase the spatial discretization, because this sometimes helps. So when we actually infuse or increase the number of spatial nodes significantly, maybe it can kind of converge. This would be the first thing. So I would go back to the graphic editor, and I go to conditions, profile discretization, and I think the maximum number of nodes is 1,000. So let's ramp it up really high, like 901. So now we have, oops, edit. So let's go 1,000, let's go the maximum number. I think it's 1,000. So now, of course, it's something different. So we have like many layers. But because this example is so simple, doesn't really kind of cut down the computational efficiency a lot. So we save this, on the So still didn't converge. But you basically saw the runtime was significantly longer because now it needs to go through each of those nodes. So this doesn't help. Next thing we can try is change the maximum number of allowable iterations, which is basically set to I think 10 right now. So we can ramp this up. So when you go to my processes, these are the iteration kind of criteria. So let's put like, so each iteration step should basically time out after 100 trials. Now it already stopped after 10. So we try to do this and see what's going to happen. You know the time you make. And this is really, when you change, only do this step by step and really start with the spatial discretization and then start changing the iteration criteria. So we say, okay. Yes?
What was the time you changed again?
I didn't change the time. I only changed the number when you go back to the iteration criteria. The only thing is what I changed is the maximum number of iterations. So initially we had only 10. So that basically means for each node, hydrus runs through 10 iterations. If it doesn't converge, it stops. Now it's going to run 100 iterations, and it doesn't converge, it stops at 100 iterations. And of course, now this increases the computational time, but all those 1T problems, they are so simple, so it doesn't really affect, like, it takes a little bit longer, but not significant. So we say, okay, and we do calculation, execute hydrus. Still didn't get
It didn't try to go to 100, did it?
Hmm?
Did it try to go to 100 iterations?
Yeah, it looks like you just
Yeah,
went 10.
it actually went a little bit longer. So you basically what you see here is the time. So we were able to simulate up to like 18 hours a little bit, but it didn't really complete till the end. So let's try to put this even higher, like 1,000. So go back to iteration criteria, put this to 1,000. But this already is like default. Right? So if you do something like this in 2D or 3D, and you wait like over until the end of the course, maybe not really. It's going to take a long time. So let's do the calculation again. Let's put this. Design thing. So it didn't really change. So one more thing we actually can try, we can actually try to kind of make the time discretization, the time steps. The initial time steps a little bit smaller. So we go back to iteration criteria. This is actually time information. So we can make the initial time step. I think the smallest is, in terms of hours, is 0.001. So we put in the smallest 0.001. If we do this, we also need to. Oh, this one is anyway smaller, so we don't need to change the minimum time step. But we also can make the minimum time step smaller, so we also can go to 0.0001. Okay. Still no solution. So this basically means because we really force that high of a flux onto the surface and we don't allow the system to kind of adjust or respond, this problem is not going to converge if we do it this way. But there is a solution to this, so we can actually, so what I want to do actually, I want to delete this one. Because now we change a lot of variables, so we
I
don't
want to skip
skip
over back
back
to
to
the
the
settings.
original one. So the only easiest way to do this is to go back to problem 4 and delete 5 and save it again. Oh. So. No, it already tells me that it's open.
Yeah, you gotta completely, I had to completely close hydrus all the way out.
Yeah, I did this,
But it's still, mine worked only once I did that. And then I had to go into the file and delete them. Where I had them saved.
You actually can close it. So when you actually go to this thing, you can close it. You only need to make sure to close number 5, then I think you can do it.
Oh, I could do that.
Now it should be, yeah. Now we only save this as 5. So now what we actually want to do, we want to allow the system to react. So instead of a system-independent boundary condition, we basically kind of apply a system-dependent boundary condition. And how do we do? Well, we can do this so when we actually go to boundary conditions, so we leave everything else the same.
Still gotta change the flux, right? Or the 2.08.
No, we need to change a lot. I mean, it's not only that. So actually the first thing we need to go is to, I think it's time information. Furthermore, we need to check time variable boundary conditions. So when you go to time information, and since we apply like a constant flux, you only need one record. So how we do this now, instead of having like this constant flux forced into the system, we apply a kind of atmospheric boundary condition. We specify this flux as precipitation. So we say okay, and then we only go to the boundary conditions. And here, first we try with atmospheric boundary with surface runoff. Surface runoff means as soon as we exceed 0 pressure on the surface, the water is removed from the system. So in this case, based on the previous simulation, basically means we cannot infiltrate everything. So we actually remove water from the system. system if you do this. So it's the atmospheric boundary with runoff. Say next. Then we have like over 24 hours. Now we only plug in a precipitation of 2.08. This is positive value. So this is a little bit the fluxes and all these things, a little bit confusing in hydrus meters. And it's not consistent with hydrus 2D, so we always need to think about this. So now we basically say we apply like 2.08 centimeter per hour precipitation over this whole 24-hour period. But at the same time, we tell the system if basically the infiltration capacity of the soil is exceeded, which leads to a pressure buildup on the surface, positive pressure, remove this water, so don't let it infiltrate. So let's see, okay, next. We don't really need to do anything to the profile, no?
So are we leaving the,
Factory again, like, it's designed like in 3, so we leave everything else. We changed to 2 times the saturated hydraulic conductivity. So now, instead of posing a constant flux, we have precipitation equivalent to 2.08 centimeters per hour. So the only thing is that we only need to run it.
So 1.04 that we were asking about.
it's gone anyway.
No, it's gone because we don't have a
Changed.
constant flux boundary condition. So there is constant
Right.
flux is out of the system.
Okay.
So now we only kind of, really the only thing we change, now we let the system react. And we apply the same kind of, basically the same flux, only instead of forcing the flux in the system, we apply like precipitation, irrigation flux, exactly the same size. And we let the system react. And we also tell the system that as soon as we exceed the pressure head of 0 on the surface, that should remove the water from the simulation. Then we run it where we actually allow kind of bonding to see the difference. So we say, okay. So in this case, you see, it's basically converging. And really the reason is because we avoided these steep gradients at the surface. We had the system react, and we basically said it should remove water if it exceeds the infiltration capacity. So now it's converging. And so we have everything, and we can copy this into our master spreadsheet. This. Observation no doubt. Do you expect a big change in the western?
It does. I don't know how to expect it, but it does.
So now, because we have like higher flux, it reacts even earlier, and because we infiltrated the highest possible capacity, the saturated hydraulic conductivity, the slope is not really different. But we start out with the higher flux, so it reacts a little bit faster initially, but then they rise because we always kind of, in both cases, we do it at full capacity, saturated hydraulic conductivity. The slope is actually very, very similar, even not identical. So in this case, then we kind of open the P-level file. So now it's basically see, it's a little bit challenging to kind of see, but you see this initially faster kind of increase to zero pressure head, and then it basically goes up to zero, and then because we tell it to remove all the water if the pressure head exceeds, so the pressure head always remains exactly at zero. But of course now the problem converges, so which is nice. So we resolved this issue like circumventing this problem somewhat. So you have those three cases now. You have like low flux, so half of the saturated hydraulic conductivity. Blue is flux that is equivalent to saturated hydraulic conductivity. Green is a flux that is double the saturated hydraulic conductivity. But in this case, we only could make it work with like, boundary condition that allows actually the system to react. So this was problem 5. So save this one. And the other thing is what 6. 6 went to repeat 5, so we copy 5 to the next page. So you see, like from 5, you see this really sharp increase. And then because we tell the system it never should let the pressure exceed 0, it remains at 0. So, okay.